I'm going to do problem number 2 from test 1, parts A and B. The problem reads, a permanent dipole and a charged particle lie on the x-axis and are separated by a distance d as indicated in the figure. The dipole consists of positive and negative charge q separated by a distance s where the length of s is much less than the length of d. The particle has a negative charge negative q and is located at x equals 0. Part A asks to determine the magnitude and direction of the force on the point charge due to the permanent dipole. The first step is to find the equation for force, which is the charge times the electric field. Here the charge is the charge of the point charge, which is negative q. The electric field can be separated into its magnitude and direction. From the formula sheet, we know that the electric field of the dipole on the axis is 1 over 4 pi epsilon naught times 2qs over r cubed, where q is the charge of the dipole, positive q. The direction of the electric field can be found in the following way. We know that the dipole exerts an electric field on the point charge. The electric field from the negative side of the dipole exerts an electric field toward the dipole. The positive charge of the dipole exerts an electric field away from the dipole. However, because the negative side of the dipole is closer to the point charge, we know that the net electric field is going to be toward the dipole, or in the negative x-hat direction. The next step is to find the position vector, which is the position of the observation location minus the position of the source. Here the source is the dipole. We see that this comes out to d in the positive x direction. We know that the magnitude of r is the square root of the sum of the squares of the position vector, which here is just d. So plugging these into the electric field magnitude times direction equation, we find that the electric field vector is negative 1 over 4 pi epsilon naught times 2qs over d cubed times x hat. Plugging this into the original force equation, we get our final answer. The force is equal to 1 over 4 pi epsilon naught times 2q squared s over d cubed times x hat. Part B asks what is the magnitude and direction of the net electric field at location A, a distance d to the right of the charged particle. Well, the first step is to figure out what the net electric field equation is, which is really just the sum of the electric field of the dipole and the electric field of the point charge. The magnitude of the electric field of the dipole is 1 over 4 pi epsilon naught times 2qs over 8d cubed, using the same formula we used earlier. Also, using the same logic as earlier, we know that the direction of this electric field is toward the dipole. So the final electric field of the dipole is negative 1 over 4 pi epsilon naught times 2qs over 8d cubed in the x hat direction. Next, we try to find the electric field of the point charge. From the formula sheet, we know that this is 1 over 4 pi epsilon naught times negative q over r squared r hat. Negative q because that's the charge of the point charge. The position vector is again the observation location minus the source, which is in this case the point charge. We find this to be positive d in the x direction. The magnitude of this is d, and the direction is the x hat direction. So, knowing the electric field of the point charge and its direction, we find that the vector, plugging in d for r, is negative 1 over 4 pi epsilon naught times negative q over d squared times x hat. Plugging both of these values, the electric field of the dipole and the electric field of the point charge, into our original electric field net equation, we find that our net electric field is negative 1 over 4 pi epsilon naught times 2qs over d squared times s over 4d plus 1 in the x hat direction, making our final answer negative 1 over 4 pi epsilon naught times qs over d squared times quantity s over 4d plus 1 in the x hat direction. Thank you for watching.